patient given a drip feed containing a particular chemical. Concentration in his blood is measured in suitable units at 1 hour intervals for the next 5 hours. The doctor believed the figures to be subject to random errors arising both from the sampling procedure and subsequent chemical analysis, but that a linear model, and that's an important point they've made there, a linear model, so straight line graph, is appropriate. So there's my little table. Find the equation of the regression line y on x. Now you already know that for the regression line I'm going to need the following values. I'm going to need b, because the regression line is y minus y bar is b x minus x bar, where b comes out to be sxy over sxx. Now we already know how to work out sxy and sxx, but to do that I'm going to need to use my table, and I'm going to need to create a new table. Now your calculator does this, and just like last time I've already got a spreadsheet with everything in, so I've used it for regression, correlation rather, so I've got all the numbers in and I can just ignore what I need and what I don't need. So let's just paste that in here somewhere. There we go. Can't ever seem to move this thing, so let's move the screen. So the first thing that I need to do is to work out what sxy is, and to do that sxy is sigma xy minus n x bar y bar. And obviously as you're doing this you are going to be putting your numbers into it, because we want to actually see these numbers. So that's going to be 130.5 minus n, and if I remember correctly there were 6 numbers in there because we had started at 0. So 6 times x bar, which is 2.5, times y bar, which is 6.6, and so this comes out to be 31.5. Next one is sxx, and again just sigma x squared minus n x bar squared. And so for sxx we have 55 minus 6 times 2.5 squared, and that comes out to be 17.5, which means that my equation for b, which remember was sxy over sxx, sxy, that's 30, that should be a decimal point in there, 31.5 over 17.5, which comes out to be 1.8. So we now shove all of that into our little equation. So y minus y bar is b x minus x bar, and so y minus 6.6 is 1.8 x minus 2.5. Rearrange it in the form y equals mx plus c, so that's y is 1.8x plus 2.1. Now generally speaking, as I've said before, we tend to write it as 2.1 plus 1.8x. Oh, so having done all of that, where's my question? All the way over here. The next bit then says, illustrate the data and your regression line on a scatter diagram. So to do that, I have prepared my autograph. Woohoo! And sure enough, here is my diagram with all my points pre-inputted into autograph. Obviously, you'd do this by hand, but it's not that difficult. Then what I would do is find out 2.1 along here and measure my gradient of 1.8. So every one along, I go 1.8 up. Now, it's not very nice to do that, so what I might do is go 10 along and go 18 up, which would be a lot easier and a lot more accurate to do. One of the joys of this is I actually have y on x regression line, and so that is the regression line, and that's mathematically what it would look like in its most perfect form. So estimate the concentration of the chemical in the patient's blood at 3.5 hours after treatment started and 10 hours after treatment started. Comment on the likely accuracy of your predictions. Now actually I don't really need to do this off the graph, but at 3.5 hours I could go up and go across. At 10 hours I could go up and I could go across. Well, I couldn't because I've not quite got it on there, but you could do it in theory. But because you've got your formula, there's actually no need to. You know that your formula, all the way down here, 2.1 plus 1.8x. So at my x value, and if you remember correctly, my x value was the time on my graph, time along the x, concentration on the y. So at x equals 3.5, I'm able to work out what the concentration is. So y comes out to be 2.1 plus 1.8 times 3.5, which works out as 8.4. Now, to comment on the validity of this, basically I have to look at my little graph. Now you'll notice we've got numbers from 0 all the way through to 5, and 3.5 is slap bang in the middle, so I've interpolated the data. Basically I can safely say between 0 and 5, actually it is a linear relationship. Just after 5, so in this kind of a region here, I could hypothesize that it could be a linear relationship, but I don't have the evidence. But as we get closer and closer to 10, well, I'm extrapolating the data. That's like me saying, oh look, I came in at 8 in the morning, by midday it's hotter and hotter. If I carry this on, then by midday tomorrow we're all going to burn and die. It just doesn't work. So at 10 hours in, it's just extrapolated too much, so the next one isn't going to be reliable. So at x equals 10, y is 2.1 plus 1.8 times 10, and so, move the screen down a little bit, that comes out to be 20.1. So this one would be reliable, and this one would be unreliable. Now obviously you're not just going to write that, you'd be looking at using the word extrapolated and interpolated, just to make sure that actually hammering home that you understand why they're reliable and why they're not reliable as well. So what's the next one after that? Calculate the residuals for each data pair, mark them on your scatter diagram, and check that the sum of the residuals is 0 and find the sum of the squares. Well, I'm going to mark them on my diagram first, and so I've copied this out, and so the residual, remember, is the vertical line from your I'm going to need a red here, vertical line from your line of best fit to your actual point. So just that line there, that line there. Obviously you're going to use a ruler, I'm trying to do this by hand, and so there are my residuals. Now I need to calculate these. Now the beauty of actually calculating them is actually you don't need to do that much more than what you've already got. Now I've been using Autograph, Excel rather, to get a table for this, and actually what I can do is work out using this the same thing. Because if I take the data that I have, and let's scroll down a little bit, I can't scroll down, so let's just leave it like this. What I do is find out the y coordinate from my line of best fit, and the y coordinate from my line of best fit, which I'm not sure how I'm going to write this because I've got x and y coordinates, so I'll just do y coordinate. I'll just write it in words. So y coord, that's going to be 2.1 times plus rather 1.8 times my x coordinate, and then let's copy all of those down. And then after that I'm going to need to find the difference between their y coordinate and actually my y coordinate. So y coordinate. So this is the theoretical one on the line of best fit, and then the other one is my original one, so I observed it as 2.4. So if I just look at my graph, 2.4 minus 2.1, whatever that is, 4.1 minus 3.9, whatever the numbers come out to be. Where's my table again? So 2.4 minus 2.1, then I can do the next one, 4.3 minus 3.9, so on and so forth. And if I sum all of these up, then they should come out to be 0. Now, they do actually come out to be 0. That number is so small that it's irrelevant. I mean, times 10 to the minus 16. So if I make it into a number and put it into 9 decimal places, you can see it's not going to be anything more than 0. So I'll just put it to a few decimal places. And then what I want to do is find this number squared. So if I just copy that, and I will find this squared, so equals that squared, and then I want to sum those as well. So there is my number as well squared, 1.520, which I'd have as just 1.52. Let's just check. Yep, nothing else. So mark on your scatter diagram, check the sum of the residuals is 0. It is. Find the sum of the squares of the residuals. We're done.